Hi class, we'll be talking about hypergeometric, binomial, and multinomial problems. Here's what's coming up in the next few lessons. All of these involve interesting applications of counting techniques. So in this lesson, I'll be talking about what's known as the hypergeometric distribution. This is a problem that involves sampling without replacement. A sister problem involves what's known as the binomial distribution, where we do sampling with replacement. So that distinguishes it from hypergeometric. We'll generalize one aspect of the binomial distribution when we talk about multinomial coefficients. Then I'll compare using permutations versus using combinations on the same problem. And then we'll look at three really cool applications: the so-called birthday problem, the envelope problem, and then for you gamblers out there, we'll talk about poker probabilities. So let's start out with the hypergeometric distribution. Here's the definition. You have A objects of type 1 and B objects of type 2. I want to select n of these, A plus B. I want to select n of these objects without replacement from the A plus B. Without replacement, very, very important. Then, the probability that I pick exactly K type 1s, and by default, n minus K type 2s, is going to be, well, this messy numerator divided by a messy denominator. The first term in the messy numerator is just the number of ways to choose exactly K type 1s out of A times the number of ways to choose exactly n minus K type 2s out of the B that are there. And then the denominator is simply the number of ways to choose n objects out of the original A plus B. At this point, it's kind of an English thing. By definition, the numerator is A choose K times B choose n minus K. That's what it's saying. The denominator is A plus B choose n. So the number of type 1s chosen, and by default the number of type 2s, is said to have the hypergeometric distribution. We'll have a very thorough discussion on what distributions means a little bit later on. Let's do a trivial example and then a less trivial example. Let's suppose we have 3 socks in a box with A equals 2 red socks, B equals 1 blue, pick n equals 3 without replacement. And so I'm picking all of them without replacements. It is trivial to see that the probability of exactly K equals 2 reds, I mean, you don't even need the equation. If I pick all 3, I'm going to pick exactly K equals 2 reds, right? So anyway, let's plug in the equation anyway. A choose K, B choose n minus K, A plus B choose n. A is 2, K is 2, 2 choose 2. B is 1, n is 3, K is 2, so that's 1 choose 3 minus 2, 1 choose 1. That's how we get the second term in the numerator. And then the denominator is A plus B choose n. 2 plus 1, 3, choose n. 3 choose 3, and the probability is 1. Makes total sense because I'm picking all 3 of these socks without replacement. Here's a less trivial but pretty easy example. Now I have 25 socks in a box. 15 of them are red, 10 are blue. Let's pick 7 without replacement. I want to know what's the probability that exactly 3 reds and therefore 4 blues are picked. A choose K, B choose n minus K, divided by A plus B choose n. You should be able to say that in your sleep now. So A is 15, K is 3, 15 choose 3. B is 10, n minus K is 4, 10 choose 4. And then A plus B, 25, n is 7, 25 choose 7, 0.1988 when all the smoke clears. Fantastic. So these hypergeometric problems are pretty easy. Let's now look at the binomial distribution. Definition. You again have A objects of type 1 and B objects of type 2. Now I'm going to select n objects with replacement from the A plus B. So in some sense, it's like repeating the same experiment over and over and over n times, because we're replicating the original conditions because we replace the stuff that we take out. So the probability that K type 1s were picked, and again, therefore, n minus K type 2s, is the number of ways to choose K type 1s and n minus K type 2s times the probability of picking K type 1s in a row and then n minus K type 2s in a row. Let me explain that. Let's look at that last probability there. So that's the probability of picking 1, 1, 1, 1, 1, and then 2, 2, 2, 2, 2, 2, 2. K1s in a row, n minus K type 2s in a row. that is a very, very specific sequence of 1s and 2s. So that's the probability of picking that one specific sequence. The first term, the number of ways to choose k-type 1s and n minus k-type 2s, that's merely the number of possible sequences. So to get the overall probability that I'm picking k-type 1s, I multiply the number of sequences that result in k-type 1s times the probability of a specific sequence. So here it is. Number of ways to choose k-type 1s, and choose k. The probability of picking k-type 1s in a row. Now, I'm repeating the experiment n times. So the probability of picking a type 1 in one experiment is a over a plus b. The number of type 1s divided by the number of anything. I do that k times, and so I get this term a over a plus b to the kth power. Then I'm interested in picking n minus k type 2s in a row. The probability of picking a type 2 in one trial is b over a plus b. I take that to the n minus k power to denote the fact that I have to do this n minus k times in a row. Okay, well that's a little messy. We're going to learn about this way more detailed later on. So the number of type 1s chosen is said to have the binomial distribution as opposed to the hypergeometric. And like I said, we're going to be discussing this in just tremendous detail later on. Let's do now the same two examples I did with the hypergeometric, but now I'm going to do them for the binomial with replacement. So I got 3 socks in a box. A equals 2 reds, B equals 1 blue. Pick n equals 3 with replacement. So I plug and chug. The probability that exactly k equals 2 reds are picked. I'm using that equation. N choose k times a over a plus b to the k, etc., etc. I get 3 choose 2, 2/3 squared, because the probability of picking a red on one trial is 2/3, times 1/3, probability of choosing a blue, to the 3 minus 2. I'm just plugging into that equation. My answer is 4/9. That is not the same as the sampling without replacement example using the hypergeometric, and it's actually a lot different. The next example, mimicking the hypergeometric from a couple slides ago, 25 socks in a box, 15 red, 10 blue, pick 7 with replacement. So this is binomial. We pick with replacement, not without replacement. The probability that exactly 3 reds are picked, use the same equation. N choose k, a over a plus b to the k, blah, blah, blah. Same equation as before. Now, n is 7. I'm interested in picking exactly 3. So 7 choose 3. The probability of a red in one individual pick is 15 over 25. To do it 3 times, 15 over 25 cubed, and then times 10 over 25 to the 4th power. That number is 0.1936. That's a little bit closer to the hypergeometric answer. It's because the sample size is bigger. There's more socks, bigger sample. That's what's going on. So what I'd like you to do for now, just compare the analogous answers between binomial and hypergeometric so you can see how they differ. We'll talk more about that later on. The last thing I'll talk about in this lesson are what is known as multinomial coefficients. For example, suppose we have n1 blue socks and n2 red socks. Then the number of assortments is n1 plus n2, the total number of socks. Choose n1. Or I could have said choose n2. It would have been the same answer. And these are just the plain old binomial coefficients that we know and love. And this is not something that we haven't already seen. The only thing that's a little different here is that I've got more subscripts on the notation, but I've done that on purpose. You'll see why in a second. What I'm going to do now, you can imagine that binomial generalizes to multinomial, and so I'm going to generalize here. Let's suppose instead of 2 different types of objects, blue and red socks, now I have k different types of objects. I'm going to let n equal the sum from I equals 1 to k of n sub I, where n sub I is the number of type I objects. Remember, I have k types, so I add them all up and I get this number n. So the number of arrangements now, mimicking the binomial coefficient, is this mess. N, and then it's a giant choose. N1, N2, dot, 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 Nk. And remember, N is the summation. This is actually generalizing the thing on the top line. N1 plus N2, choose N1. This generalizes that. And in fact, the definition of this so-called multinomial coefficient is n factorial over n1 factorial, n2 factorial, times, nk factorial. This is the number of possible arrangements of the blues and the reds. Okay, and here's the cool example that everybody learns in their first probability course. How many ways can the letters in Mississippi be arranged? Okay, before we do anything, it turns out there are 11 letters in Mississippi, and if we had subscripted every one of them, I guess that means that there are 11 factorial ways that we could arrange all these things, but we don't see the subscripts. The I's look the same to us, the S's look the same, the P's look the same. So we're going to have to try to figure out how many ways can we arrange all those letters to make unique words. Okay, well, the number of permutations of 11 letters is 11 factorial. But now we have to divide out the redundant, the repetitive numbers. So we divide out the number of m's factorial, which is just 1, the number of p's factorial, which is 2 factorial, the number of i's, 4 factorial, number of s's, 4 factorial. Because I can arrange, for instance, the number of s's 4 factorial ways, but they all spell the same word. They spell, they're still going to spell Mississippi. So the number of ways to do this is 11 factorial over these correction factors. 1 factorial, 2 factorial, 4 factorial, 4 factorial. You can still arrange that messy word, 11 letters, 34,650 ways. And there you go. Okay, fantastic. So we're going to be having lots of other interesting applications of counting problems coming up in the next few lectures, and you'll be interested and amused in those. So I invite you to come back as soon as possible. So see you soon.